Okay, welcome to today's class. This will be the last session we have before the first exam, and also covering the last bit of material that's included on that. So we're going to finish chapter 3 today. We will start chapter 4, which is not until the next exam. But the major focus, of course, today is on nomenclature, which is talking about how we're going to name ionic and covalent compounds. All right, so we're going to start with, ionic compounds today. Now, there is some information there that in the tables in your book that you'll need to be familiar with. We're going to cover what I think is the essentials and the important stuff today. But there are some also textbook information that's useful to look at when you're learning this stuff. So we're going to start with ionic compounds. The first thing to recognize, if it wasn't obvious at this point, is how do we know when something is an ionic compound? So an ionic compound is going to combine a metal with a nonmetal. So if you just look at the formula of the compound, it will have both metals and nonmetals in the formula. And we're going to start with what are called binary ionic compounds, which are ionic compounds that just have two elements only. So one metal, one nonmetal element in different ratios. And how do we name those, and how do we write their formulas, which we've already talked about a little bit. Okay, so the first thing is that when you name an ionic compound, there's, as I said, going to be a metal and nonmetal involved. And so you're going to put the metal first in the name. So the names will be typically two words, and the metal will come first. That's, again, the element that would form the cation in an ionic compound, as we talked about earlier. And then the nonmetal comes second in the formula. And that's going to be the element in an ionic compound that would gain electrons to form an anion. Okay. This ordering applies to both the formula and the name. So we already talked about how to come up with the chemical formulas for ionic compounds by predicting the charges of ions and balancing them with appropriate subscripts on each element. And in that situation, you put the metal first and the nonmetal second, and that's also going to be true when you name ionic compounds. So when you're naming an ionic compound, there's two parts of the name, the cation and the anion. So for the first part of the name, the cation, you just take the name of the metal unmodified. So as we learned earlier, sodium, which is in the first column of the periodic table, we will predict would form a +1 cation whenever it makes ionic compounds. And so it's going to be in the formula as Na+, formally, but you will just name it as sodium. So when a metal forms a cation, its name doesn't change. Is the short way of saying that. Or calcium 2+, still just named as calcium. Now we'll talk in a couple slides about some situations where you put something else with the metal's name, but you don't actually change the name of the metal. It just goes in as is. Now for the anion part of the name, for the second part that comes from the nonmetal, you use the root name, the root part of the element name, and then you add on an IDE ending. So if you had an ionic compound that included fluorine, F is in the second to last column of the periodic table, so we would predict a -1 charge for that anion, F-. And when it's in an ionic compound, that would be named as fluoride. So again, fluor being sort of the root part of the element's name, but then instead of calling it fluorine, we call it fluoride with an IDE ending. Or if you have an ionic compound that includes oxygen, we would predict a 2- charge, and we name that anion as oxide, IDE, or N3-, nitride, etc. All right, so again, this is what we do for binary ionic compounds, where there's a metal cation and just a single nonmetal in the formula that forms the anion. And for the second part of the name, you would put IDE as the end. Now, in the formula, you're going to have subscripts involved. This we already talked about, but this is just a quick review of that. So you don't put any subscript or numbers in the name. But in the formula, you're going to have subscripts that designate how many cations, how many anions you have, how many metal atoms, non-metal atoms. And as we talked about before, you want to use the lowest whole number ratio. So we'll review a little bit about the formulas of compounds as well today, which we've already talked about. So this is not new, but when you make an ionic compound and you designate the formula of that compound, it should have the smallest whole number ratio of the two elements that are involved. Okay. So let's give a bunch of examples of binary ionic compounds. So MgCl2. Now again, to come up with the name of the compound, you don't really need to figure out what the charges of the ions are. You can just look at the elements that are involved, and that'll give you the name directly, regardless of the charges. But if we add MgCl2 as just as a reminder, let's get the periodic table up for a second. All right, so MgCl2, magnesium, Mg is over here in the second column, so we would predict a +2 charge for that cation. And then Cl, chlorine, in the halogen group, second to last column, would acquire a -1 charge to reach the noble gas configuration. So you don't have to do it in this much detail, but this is a helpful review. So we will predict Mg2 plus, Cl minus, and that's why there's 2 chlorines in the formula to balance those charges, a 2 plus from the metal, 2 minus ones from the non-metal. But the way we name it doesn't really take consideration of that. The metal is magnesium, so that's going to be the first part of the name. The non-metal is chlorine, but we always put the IDE ending on those. So it would just be magnesium chloride. And so again, a key part of ionic compounds that's a little bit different than what we'll talk about later with covalent compounds is you don't need to put anything in the name that indicates how many of each ion there are. Because magnesium will always form +2 cations, chlorine will always form -1 anions. So by that knowledge, the ratio has to be 1 to 2, so you don't need anything in the name to tell you that that's the ratio of those two. It's just magnesium chloride, even though there's 2 of the chlorides in there. Okay, and then we have CS2O. Cesium, we wouldn't need to know the name of that because it's too far down the periodic table, but CS is cesium, and it's again a group 1 cation, so +1 charge. Oxygen over here, we already gave the example earlier, but there's it's in group 6, so it acquires 2 electrons to get to a noble gas configuration. So you're going to have 2 cesium pluses and an O2 minus. But again, we don't really need to worry about that to name it. We just put the metal first, which is cesium. Oxygen becomes oxide as an anion, keeping that IDE ending. All right. So in homework, in test questions, we could ask you to go in both directions. So we could give you the formula, ask for the name, or we could just give you the elements and ask you for the name or the formula. So again, coming up with the formula for these compounds is something we reviewed last time, but we'll cover it again. So strontium and iodine, I think strontium is also further down the periodic table than you necessarily need to know, so apologize for that. But strontium is here, SR. It's beyond 36, so we don't expect you to be able to know the name of that one. That'll be given on the exam. But anyway, SR is strontium, so it's a +2 cation because it's in the second column, paired with iodine, which is I, -1 anion. So those are the 2 charges you would have, SR2 plus and I minus. And as we said, the sort of thoughtless or no-brain way of coming up with the formula is just to take the charges and cross them over and make them the subscripts on the other element. So the -1 on iodine becomes just a subscript of 1 on strontium. The +2 becomes a subscript of 2. So SRI2 would be the correct formula that balances the charges. And again, the naming is quite straightforward for binary ionics. The name of the metal, which is strontium, which we gave you here. And then iodine takes on the IDE ending as iodide. All right, and then sodium sulfur, maybe a more reasonable example since these elements are of the 36 that we expect you to be able to match name and symbol. You'll always have the periodic table, but the periodic table only has the symbols, so you do need to know the names of the first 36 elements and the symbols that go with them. So for sodium and sulfur, sodium is Na. We already talked about that one at length today. So +1 cation in group 1. Sulfur just below oxygen. So by the same argument as oxygen, we expect a -2 anion, gaining two electrons to get to the argon configuration. So we start with those charges when we're coming up with the formula, Na plus S2 minus, and again, just crossing the charges over to make them subscripts gives us a formula of Na2S, and the naming would just be sodium is the metal, sulfur becomes sulfide. Okay. All right, so those are again are binary ionic compounds, and especially when they involve main group metals. The first two columns of the periodic table paired up with some anion for the non-metal series. You just have to name the two elements and change the second one to have an IDE ending. So it's pretty straightforward. Things get a little bit more complicated with transition metals, which we won't do as much of in this class, but it still is fair game from a nomenclature standpoint. So the rules for transition metals are very similar. So I don't want to say that there's a whole new set of rules you have to worry about just because there's a transition metal in the formula. As we'll see, there's just one little thing that goes differently with them. The formula follows the exact same convention. Cation, then anion, balance the charges. So nothing's different about the formula of an ionic compound if it includes a transition metal. And you use, again, the smallest subscripts to balance the charges. The difference with transition metals, which we haven't talked about a lot, but maybe already something you're aware of. Transition metals don't have nice, predictable charges that they form when they make ionic compounds. So, classic transition metal, iron, Fe, there's no way to easily predict what charges it's going to form. And in most transition metals, there's more than one possible cation that can be formed. So what we do then in that case, because in most transition metals, there's different kinds of cations that can be formed with different charges involved, the name of the compound is going to include a Roman numeral in parentheses that designates the charge of the metal in that specific compound. So that comes after the metal's name, which again does not change, but it includes now a Roman numeral that indicates what the charge of the metal is, because it's not easily predictable for transition metals, and most of them, the metal can form more than one different possible charge. So as an example, we talked about iron already. Iron has very commonly formed +3 cations in ionic compounds. And so in the name of that compound that involves that, you would write iron with Roman numeral 3 in parentheses. But then iron can also form a lot of compounds where iron has a +2 charge. Again, both of those are possible. That's not something that is easily predictable or that we necessarily expect you to memorize, but that's the situation with transition metals. So it forms, both of these are very common. There's some less common ones with iron as well, beyond +2 and +3, but these are the two most common. But whatever the situation is for transition metals, you put that charge in parentheses. So if you have the formula of the compound, you can get what the charge is because you'll know the charge on the anion, and you'll just have to figure out what charge does my metal need to balance that. But if the name is given to you, then the name will include those Roman numerals to tell you what the charge of the metal is, which you otherwise would not know. Now, something that we won't necessarily test you on, but that I want you to be aware of just because you might read different sources about chemistry, or you'll see this in labs sometimes, and so I don't want it to be a totally foreign thing to you, is that there's some old school nomenclature out there that, again, is not going to be tested in this class, but that you'll see, where we don't just use this Roman numeral convention. We actually give different names to the metal depending on what its charge is. It's not always used, but for some metals it's common. And so when you see this situation, it typically occurs when a metal has two common charges that it can adopt. So like iron +2 and +3, copper +1 and +2 is another one. And so the one that has the higher charge, which would be +3 for iron, would get an IC suffix. And in this old school naming system, it also keeps the Latin name where the symbol comes from, Fe. So if you see a compound that has Fe3+, it could be named as ferric. So iron 3 chloride or ferric chloride would be the same thing. Again, not expecting you guys to necessarily know this, but just for familiarity. And the one that has the lower charge, which for iron would be +2, has an OUS ending. So cuprous if it's copper 1, or iron 2+ would be ferrous. Now, another reason for giving you this information now is because I like jokes. And so what would this carnival ride be called here? A Ferris wheel. So now you remember that. Okay. So that's a Ferris wheel, an inorganic chemist's favorite carnival ride. All right, but you don't, again, you may see that from time to time in your everyday life or in other science courses that use chemistry, but it's not something in this class we expect you to be responsible for. But the Roman numeral system that is a little bit more straightforward to use is something that could definitely come up. Okay. So we'll give some examples of that in a little bit, but in the meantime, I also want to cover polyatomic ions, which can sometimes come up in formulas for ionic compounds as well. So a polyatomic ion is, these are going to be groups of covalently bonded atoms. So we did one of these, or maybe more than one of these in last class when we were drawing Lewis structures. We drew the Lewis structure of NO3 minus. So that's an example of a polyatomic ion. It's a group of covalently bonded atoms, but that group of atoms has an overall charge. So they are ionic in nature. Almost all of the ones we expect you to know are anions, as it turns out, negatively charged, but there are some that are cationic as well. Okay, so I hope the table number that I gave you is still accurate. They update the textbook from time to time, and I don't always closely read it, but somewhere in chapter 3, I think it's 3.5 or somewhere thereabout, there's a table that has all the ions we expect you to know. So you'll need to know the name of the ion, the formula, and the charge that are associated with it. And it might look like a lot. I'm not going to pretend like it's a tiny amount of information. As you go through the homework questions and the quiz questions and the review problems and all that stuff, you'll start to get a sense for which ones are most common. So obviously there's some that you're going to see a lot more than others. Make sure you know those ones because they come up a lot. Some of them less common. You'll kind of get a feel for that the more of these practice problems you end up doing, and you'll kind of get a sense from that from today's class a little bit as well. All right. Now, the thing with polyatomic ions is that sometimes this leads to the inclusion of parentheses in the formula. So in a regular ionic compound that just has a metal and a nonmetal, you just put the two elements in, you have subscripts in there, but no parentheses. For polyatomic ions, if the formula of the compound has more than one of those, so it really only comes into play in the formula, not the name. But if the formula has more than one polyatomic ion, so for example, nitrate, if there's two of them, we're going to give an example about that today in a little bit. If there's more than one polyatomic ion, it's enclosed in parentheses to indicate that those atoms are all grouped together as a single ion. Once you write it out, it'll be pretty obvious why we do it this way. It's very confusing if you don't. We have to remember to do this, and if you see those parentheses, that's what that's referring to, is that group of atoms exists together as a single polyatomic ion, but if there's more than one of them in the formula, you're going to have them in parentheses, and then the subscript that tells you how many of those are will be outside those parentheses. Okay. All right. So if there's only one ion in the formula, you don't need to do this. So if we have sodium plus making an ionic compound with nitrate, which is NO3 minus, one of the most common polyatomic ions that we'll see in this course, there's just one of each to balance the charge, plus one cation minus. So you can just write the formula as NaNO3. That's typically how you see it. Now, in my mind, I wouldn't consider it wrong if you put parentheses around the NO3. They don't have to be there. And also, I'm not sure if WebAssign has the same opinion about that as I do. It's not. I don't think it's really wrong to put parentheses. We don't need them if there's only one in the formula. But in cases where there's more than one in the formula, then the parentheses are a necessity. So if we made an ionic compound that instead of having sodium had calcium 2 plus with nitrate NO3 minus, again, we can come up with the formula the same way as we typically would, where we take the charge on one and make it the subscript on the other. This time, that -1 charge is associated with that whole NO3 unit, the nitrate. So that comes up with a formula then where you would need 1 calcium and 2 nitrates to balance the charge. So you would write it in this way. There's NO3 minus, but there's 2 of them in the formula. So the whole thing goes in parentheses with that subscript on the outside telling you how many there are. And again, it would be very confusing to try to write it any other way. So if you try to write it as CaNO3-2, that looks like NO32, which is very confusing, right? If you don't have the parentheses there. Or you don't want to sort of distribute and combine things. You don't want to write it as CaN2O6 because in many situations, N2O6 means something entirely different than NO3, and you lose the information about having nitrate in the formula if you just try to glom everything together like this. So even though this is the chemical formula of the compound, it's not the correct way to write it because you lose the information about having NO3, having nitrate present. So don't try to write them like that. Use the parentheses whenever there's more than one in the formula. All right, so now we're going to go through some other example problems where we name compounds. So if we have Fe2O3, so when we're dealing with transition metals, so again, if it wasn't obvious, we already talked about it a bit, but Fe is right here in the middle of the D block. So it's clearly a transition metal. And so we need to make sure then that the name of that compound designates the charge of the metal in parentheses. That's the key difference when you have a transition metal in the formula, is to make sure you include the charge. So for Fe2O3, it's not obvious from the formula what the charge is, so you have to come up with that. So we have 2 irons in the formula. Oxygen is always going to be O2 minus. We talked about that one earlier. So in these ionic compounds that involve transition metals, you never change the charge on the anion. It's just the charge of the metal that's variable. So we have 2 minus oxygens. We have 3 of them in the formula. So if we want to balance these charges out, 2 minus charges on oxygen is a total of -6. You need to have +6 from the metal. If there's 2 of them, each of them has to be +3. So again, a little bit of working backwards, a little bit of algebra to come up with. This compound has iron 3+. If the iron was any other charge, the charges wouldn't balance. So in order to have a fully balanced formula, if you have 3 -2 anions, you need to have 2 + 3 cations. So again, each of those would be 6 minus 6+. So then the way that we would name this is we start the name with iron, which is the name of the metal. But because it's a transition metal, we have to indicate with parentheses that this is a +3 charge with a Roman numeral. And then the anion, we don't do anything to, we just still name it as oxide. So again, this part here, which I'll underline in red, is the only difference when you're including a transition metal in the compound. You have to include that in parentheses to indicate that. All right, and then the other one that I gave you here is CuSO4. All right, so for this one, we have copper, which is the metal, and Cu is over here towards the right, but still in the transition metal series. So it's another one that requires us to indicate the charge. So we don't know what that is off the bat. And then we have the anion in this case is a polyatomic anion, which you would need to recognize. SO4 as a polyatomic anion is SO4 2-, and we call that sulfate. So again, you have to learn sort of the formulas, the charges, and the names. They all kind of go together as you're familiarizing yourself with this. And a lot of students get, frustrated about this, like, oh, I can't believe I have to memorize all these polyatomic ions. Well, I view it as learning to speak the language of chemistry. If you're going to succeed in any field, you have to learn the language, and learning polyatomic ions is part of the language of chemistry. So view it in those lens. Maybe it sounds a little bit better than memorizing. All right, so we have those involved. So anyway, it's SO4 2-, so that means the charge on the metal has to be 2+ to balance that. There's one of each in the formula. We have 2- from the polyatomic anion, so 2+ from the metal would balance that. And so then we would name this as copper is the metal, 2 in parentheses to indicate a +2 charge, and then the name of the anion in this case, which is polyatomic, is sulfate. So for the polyatomic anions, they have variable endings. Most of them are ite or ate for the anions, but there are exceptions to that. And you don't change the ending on those polyatomics. So that you just need to know the name, and it just goes straight into the name of the compound as that. You don't ever alter the ending to IDE or anything like that. It's just going to be sulfate. If we change that to sulfide, that would mean something totally different. That would just be S2-. So you have to keep the name of those polyatomics exactly as they're given to you. Those don't ever get altered. And there is a little bit of a pattern to this too that you should hopefully recognize. So a lot of compounds, a lot of polyatomic anions are what are called oxoanions, where you have some atom at the center surrounded by oxygen. So NO3-, SO4 2-. And in some of those, you would have 2 possibilities where you have different numbers of oxygen. So you have SO3 2- and SO4 2- as an example with sulfur. Both of these are polyatomic anions. When you have that situation with different numbers of oxygen atoms, the two have the same charge. You don't have to remember that there's different charges involved, but the names are a little bit different. And the one that has fewer oxygens would have an ITE ending, so it'd be sulfite. And the one that has more oxygens would have an ATE ending, sulfate. So you'll see that with nitrite, which is NO2 minus, and nitrate, which is NO3 minus, sulfite, sulfate. You have a larger series with chlorine, which is hypochlorite, chlorite, chlorate, perchlorate, phosphite, phosphate. So there's that pattern, different numbers of oxygens involved. So you have to, again, become familiar with that. But a little bit of a pattern when there's two possibilities or more than two possibilities like that. Okay. All right. And then finally, just working backwards now from the name to the formula. With ionic compounds of transition metals, this is actually more straightforward because the name directly gives you the charge. So all you have to do to come up with the formula is make sure the charges are balanced, which is usually pretty straightforward. So if we have chromium-3 permanganate, chromium, the symbol is Cr. That's one you need to be familiar with. It's a 3+ charge. And then permanganate, probably don't know it yet if you haven't studied this part of the book yet, but permanganate is MnO4 minus. It's one of the only polyatomic ions that also includes a metal in the formula. So there's permanganate and there's chromate and dichromate. So there's a few of those that involve metals, and this is one of them. So it's, again, a cation and an anion with a polyatomic anion in this case. So we can balance those charges by making the charges into subscripts. So you would need 1 chromium and then 3 permanganate. So that's going to go in parentheses to balance that charge. I'm not sure if this compound actually exists, but it's fine to name it. All right, and then finally, tin 4 chloride. I think tin is beyond where we expect you to know. Yeah, it's number 50. So if you didn't remember that the formula, the symbol for tin is SN, we would have given that to you in context. But SN is the symbol for tin. And just like transition metals, I don't think your book covers this in a lot of detail, so it's not likely to come up, but some of the main group metals on the right side of the periodic table, so like tin, lead, indium, some of those that are like on the bottom of the P block, some of those also have the possibility of forming multiple charges, so you would have to indicate that. So tin is one of them, which can form +2 or +4. So tin 4 would be SN4 plus, and then chloride, as we've already seen multiple times today, is Cl minus. So again, to make a balanced formula, you would need 4 chlorides to balance the charge of the metal. So SnCl4. All right. But again, if you're going name to formula, in situations where the charge of the metal is given directly to you, you just need to remember what the charge of the nonmetal part is and balance them out, and that gives you the formula. So there's not as much to it there. All right. Any questions on naming ionic compounds? We finished that part for today. All right, so we'll move on to covalent compounds. So for a covalent compound, we're talking about compounds that have only nonmetals in the formula. So again, to recognize whether it's covalent at this stage, you just look at the formula of the compound. If it combines metals with nonmetals, it's ionic. If it's nonmetals only in the formula, then it's covalent, and you would follow then this naming scheme. And the big difference between naming covalent and ionic compounds is that in covalent nomenclature, we do use prefixes to indicate how many of each of those elements is in the formula. Because in many situations, you can have, and this came up earlier in the course with law of multiple proportions, you can sometimes have 2 different covalent compounds that have the same elements involved but different ratios. So you can't have the same name for those 2 compounds. That would be confusing. So we put prefixes in the name to tell us how many of each atom we have. So a common example that you've likely encountered is carbon and oxygen can make CO, which is carbon monoxide, or CO2, which we named as carbon dioxide. So we use mono and di prefixes to indicate whether there's 1 or 2 oxygens in the formula. And so that's going to be the key difference here. You don't use these prefixes at all with ionic compounds, but in covalent compounds you do. We're really only going to talk about what are called binary covalent compounds, which are just compounds with 2 elements, and that's where these prefixes need to be used. So if there's 1 element in the formula, you would use mono. Just as a note, this is only going to be used on the 2nd element in the formula or name. So if the first element in the formula, there's only 1 of them, you just name the element without the mono. It's implied in that case. And that's why carbon dioxide is not monocarbon dioxide, it's just carbon dioxide. But then carbon monoxide, CO, would be carbon monoxide because you don't put the mono on the first element, but you put it on the second. So you only use this one on the 2nd element. So be aware of that. All the rest of them you would use in any situation. So 2 is di, 3 is tri, 4 is tetra, I forget if these are Greek or Latin, but the Greek, but most of them anyway. But they're fairly familiar in other contexts as well. Penta, hexa, hepta for 7, octa for 8, like octopus, nona for 9, deca for 10, and that's as high as we'll go. So those prefixes will tell you how many of each element are in the formula for a covalent compound, 1 through 10, mono, di, tri, tetra, and so on. All right, so those are going to be used for, again, a class of covalent compounds that are called binary covalent compounds. So these are going to be covalent compounds that have 2 and only 2 elements in the formula. So exactly 2, I should say, is maybe a better way to say it. And there are 2 different elements, of course, you can't do the same. So 2 different elements, exactly 2 different elements in the formula. All right. Now, again, when we're naming these, there are rules associated with which order the atoms come in. I really don't think you're going to have to remember these rules because we're going to just give you the formula and ask you to name it, and you just name it in the order that's given in the formula, right? So there are rules. I would give you the rules just so you're aware that it's not totally random. But again, you won't really have to worry about these rules because in homework and test questions, you should see that you're just going to get the formula, produce the name, and you just put the name of the elements in the order that they come in the formula. So it's already kind of stated for you. But the first element in the name or the formula is going to be the one with the lower group number. So these are used for, again, the P block elements where groups, I guess, 3 through 8 over on the right side of the periodic table. And the one with the lower group number comes first in both the formula and the name. So again, the classic carbon monoxide, carbon dioxide example. Carbon is group 4, oxygen is group 6, so carbon comes first in both the name and the formula. Now, if the 2 elements are in the same group, so if you have like sulfur and oxygen together in the formula, for example, which are both group 6, then you would use the one with further down the periodic table, the heavier one. The higher period or the heavier one, if you think about it that way, comes first. And we did an example in class last time of a Lewis structure of SO3, again, a compound of sulfur and oxygen, which are both group 6 elements, or IF5. Sulfur is further down the periodic table than oxygen. I don't have a periodic table here, but I'll show you. You don't believe me. So again, sulfur right here, oxygen right here. Oxygen is a higher period number. It's further down the periodic table. So that element would come first in the name of the formula. So it's SO3, not O3S. And the name would be sulfur trioxide, not trioxide sulfur. And similarly, IF5, we put iodine in the formula in the name first because iodine is further down the periodic table than fluorine. So that's the rule that you follow if they're in the same column of the periodic table. Okay. And we still need to put an IDE ending on the second element. So even though it's not ionic anymore, that part of the naming system still gets preserved, where the second element that we name, second element in the formula in the name, would have an IDE ending when we produce that name. All right, and again, the key differences between this and ionic compounds is that we use those prefixes to denote how many of each there are. And then when we talk about the formulas of covalent compounds, resist the urge, resist the temptation to reduce them to the lowest whole number. Leave the formula as is. And just directly translate name to formula if that's what you're asked to do. Don't try to reduce the formula in any way. And this is because, as an example, NO2 and N2O4, if you reduce the formula of N2O4 to its lowest whole numbers, it would also be NO2, but those are 2 different compounds. So we can't just go about reducing formulas of covalent compounds because often that then changes it to a totally different compound. So if you're given the name of a covalent compound, the prefixes in that name directly tell you how many elements of each there are, and you just directly translate that to a formula. Don't do any reduction of those or any changes on those coefficients at all on the subscripts. All right. So we'll do some examples of binary covalent compounds. So if I give you the formula, you would have to give the name. If I gave you the name, you'd have to give the formula, work both directions, and that's really the level that we would expect you to do this at this point. So SF4, you need to know the names of the two elements, which are sulfur and fluorine. You name them in the same order that they're given in the formula. So it starts with sulfur. Again, there's one sulfur, but you don't use that mono prefix if it's on the first element. So again, while it may not be technically wrong to say monosulfur in this case, it's not conventional, so you would want to leave it off. And then there's 4 fluorine. So the prefix that means 4 is tetra. And then again, you change the ending to IDE. So it wouldn't be sulfur tetrafluorine, it would be sulfur tetrafluoride. All right, tetra tells you there's 4 in the formula, IDE on the second element only. And then in this example here, P2O5, the 2 on phosphorus tells us that it should have a prefix of di. The 5 on oxygen should have a prefix of penta. And so when you name this, you just need to put the prefixes in front of each element. First one, the name doesn't change, phosphorus. And then this is one where I would be forgiving because this isn't a spelling course, this is a chemistry course. Either pentaoxide, or sometimes if the name of the element starts with a vowel, you leave the A off. So you could say pentaoxide or pentoxide. I would not. If you get marked wrong because of that, let me know and I'll fix it for you. But I think it'll count both in our class. So you could either call it pentaoxide, or a lot of times that A is left off if the atom that is modifying, the element that's modifying starts with a vowel like it does here. Okay, diphosphorus pentoxide. I think named a formula is even easier because you just need to know the symbols and the prefixes. So nitrogen trichloride, nitrogen is N, chlorine is Cl, tri means 3, so NCl3. Pretty straightforward to go from name to formula. And then disulfur decafluoride. Di means 2, sulfur is S, fluoride F, deca means 10, so S2F10. And again, you would write this exactly as S2F10. You wouldn't try to reduce it to SF5 or anything like that. Keep it exactly as it is for a covalent compound. There's no simplification needed for those. Okay, so any questions on binary covalent compounds? Okay, that's probably the easiest class that we'll name. And then the very last category of compounds that we want you to be able to name at this point are acids. Now we're going to talk about the chemistry of acids in chapter 6, so a few chapters from now still. But for now, we just need to recognize them and know the names. Now, first to recognize what compounds are even classified as acids. It's a covalent compound, but it's a special type where you have a polyatomic, or any really different types of anions. Most of them are polyatomic, but there's some that are binary acids as well. But you have an anion, so a nonmetal anion, but instead of being paired with a metal like it is in an ionic compound, it's paired with hydrogen, which can be formally thought of as H+ in this situation. Even though hydrogen is a nonmetal, it can behave like H+ when it's in acids, and we'll talk in more detail about that in chapter 6. For now, I just need to recognize that the formula of an acid will start with H. So if it starts with H, unless it's like water, for example, which you all know is H2O, if it starts with H, typically it will be thought of, you want to just zoom in on it being an acid and name it as such. So there's 2 types of acids. Binary acids are just H+ with a monoatomic anion. So again, just a nonmetal anion, like typically from the halogen series are most of them. So the F-, Br-, Cl-, I- are the most common ones. So really the only ones you should know at this point are HF, HCl, HBr, HI. So again, hydrogen paired with any of the halide anions, F-, Cl-, Br-, I-. And the only other one that's really classified as an acid that has this type of formula would be H2S, hydrogen with sulfur. There are other nonmetal compounds of hydrogen, but they don't behave as acids, so we don't classify them as such. So just make sure you remember all the halogens plus sulfur gives you a binary acid, as it's called. So when we do this, when we name these binary acids, the name is a little bit complicated, but you have to put a prefix on the element name, which is hydro. Then you put the root name of the anion in there, all as one word. So hydrogen, the root name of the anion. You follow that with IC. So this is all one word. And then a second word, acid at the end. All right. Okay, so as an example of these ones here, HCl, you start with hydro. Chloride is the anion, so use the root name of that, which is chlor. But instead of "ide," we use the IC ending, and second word, acid. So hydrochloric acid, hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, hydrosulfuric acid, okay? And if it starts with hydro, that's the key giveaway that this is a binary acid, which only has 2 elements in the formula. Now, another major category of acids that we'll see are called oxoacids. This is where, you still have H plus at the start of the formula, but it's going to be paired with what's called an oxoanion. Oxoanions are those many different types of polyatomic anions that have a center atom with oxygen around them. Nitrite, nitrate, sulfite, sulfate, chlorate, perchlorate, all the ones that have center atom with oxygens around it are called oxoanions. And if you pair those with H plus, you make what's called an oxoacid. So HNO3. In the formulas of these, you need however many hydrogen atoms is the number needed to balance the charge. So if you had sulfate as the anion, SO4 2 minus, has a 2 minus charge, so that would have 2 hydrogens in the formula. All right, so if you're coming up with the formulas for acids, you just need to have H as formally H plus, and you just need to have enough H pluses to balance the charge on the anion. So for sulfate, which is SO4 2 minus, 2 hydrogens. So the way that we name these is you just use the root name of, again, the anion, which is polyatomic in this case. You change the name of that to either IC or OUS, and I'll define which is which here in a second. And then again, acid at the end. So if it's an 8 anion, that becomes an ic acid. So if the anion name ends with 8, the acid name has IC in it. And if the anion name ends with ICE, it would be an OUS acid. So maybe to give you one example of each, let's change this to H2SO3. So HNO3 would be nitric acid. Nitrate changes to nitric when it's an ATE ending. And then this one here, the sulfite, so it becomes sulfurous acid, or sulfus acid is fine as well. All right. But if it's so the name of the acid, the ending comes from what the anion is. All right. Again, you'll see some of these are more common. Sulfurous acid is not very common, but nitric acid very much is common. Same with sulfuric acid. All right. So just ending with the nomenclature section with a couple of examples. What's the molecular formula for hydrofluoric acid? So again, if you're looking at the names of acids, if you have hydro in the name, that immediately identifies it as a binary acid, which means there's only 2 elements in the formula, no oxygens, just hydrogen with some nonmetal. So that takes out already these 2 here. And then again, you have choices A and D left. That's the only ones that are even binary formulas. And in acid names, we always put hydrogen first. So this is the correct way to do it for hydrofluoric acid. So all formulas for acids will have hydrogen at the beginning, then the anion comes after that. And the formulas kind of look like ionic compounds, but they start with H instead of with a metal. All right, so that's HF, hydrofluoric acid. And then this one here, H2CrO4, what's the proper name for that? So again, getting the names of these oxoacids correct requires you to know the names of the anions. So CrO4 2 minus, and you know it's 2 minus in this case because there's 2 hydrogens in the formula, so that much is clear. But the name of that anion is called chromate. And again, you may not have learned that yet. You have time, but you have to make sure you get familiar with all these names and formulas for polyatomics. And when we name an oxo acid, you don't put any prefixes on this. You just change the ATE to IC or the ITE to OUS. In this case, is ATE, so it becomes chromic. And then you just add acid at the end of the name. All right, so again, no hydro prefixes when it's a oxo acid. And then the correct one here would be C, chromic acid. Chromust would be if it was a chromite anion, which I don't even think exists. Perchromic doesn't exist either, so it's going to be chromic acid. All right. So any questions on nomenclature? Because I think I have a bunch of tables now. Yeah, here's a bunch of tables that are reproduced from the book. I don't think anybody opts out of the textbook anymore because you have CTAP, but in the past, there were a lot of students that thought the textbook wasn't important enough, so they didn't get it. So there's those tables. Any questions on nomenclature before I close up chapter 3 and exam 1 material? Yeah. No, Monday's a regular class day. So some people will be taking the exam on Monday. Again, there's some luck involved with what day you get, which I have no control over. So don't blame me if you don't like your exam time. But Monday, there'll be some people taking the exam, but everyone else will have class if you're not taking the exam. It is a regular class day. The only time that I'll give you hints and information about possible pop quizzes is that I won't do them during exam weeks, only because I know some students have no choice but to take the exam during class time, which is not ideal, but I know it's sometimes unavoidable. So there won't be any pop quizzes, but you're still encouraged to come. We're going to be covering new material that's still going to be valid on the second exam. But the only review that we have is outside of class. So I have materials posted in Canvas right under the lecture notes, which are it's like a practice exam, solutions, and a video that I recorded a couple years ago where we covered those topics. So that's going to be the review material that I provide. Plus, there's the practice exam for Web Design. But there won't be any class time devoted to review, except for maybe at the very end of the semester if we finish everything a little bit early. Now, one thing I'll kind of say about class next week, since the question came up, I expect the room to be given historical norms, probably about half filled at most. Well aware that's going to happen. It's not going to be a shock to my system to see most of you not here next week when you're focused on the exam. But I will also say that the material that we cover next week, which is most of chapter 4, is the material that on the second exam, people often do the worst on because they were skipping class while it was covered and focusing on exam 1. So I know it's tough to balance everything. I'm not downplaying the challenge, but try to be here, try to keep up with what we cover next week nonetheless, because it's still new stuff. It's still going to be on the exam too. And many students do struggle with that because of their lack of attention during the exam week on what we're learning currently. So that's my warning to you. But I will also put in the notes right here, just in case it's not obvious, this is the end of exam 1 material. I don't know if we call them exams or midterms these days, but whatever that first exam is that you're all focused on next week, any material before this is covered on that. Anything we're going to cover the rest of today with the little time we have left would be only covered on exam 2 in the final. So any last questions on chapter 3 or anything? Yes. Yes, I believe that should be posted somewhere in Canvas, but it looks exactly like this. So I think CASA has, I don't remember if, so I believe CASA might have hard copy printouts of them posted on the workstations. I don't know if they still do that. They used to. And then I think at the beginning of the exam, which I think you've probably also seen it on the homework and quizzes, this exact periodic table will be like posted there in the beginning of the exam. So if you have to scroll back up to it, you can always look at it. There might be hard copies also posted at the workstation. I'm not sure if CASA does it anymore or not. Okay, any other questions? Okay, so we're going to go on to chapter 4. So chapter 4 kind of progresses nicely from a lot of things we covered in chapter 3, and especially stuff related to covalent bonding. And what it's going to cover is, first, we're going to start with the shapes of molecules. So when molecules form covalent bonds and form and assemble, what is the three-dimensional arrangement of those atoms in space? That's one topic. And then we're going to talk in more detail about how those covalent bonds are formed in terms of the atomic orbitals and how they overlap and change in different ways to make bonds. So chapter 4 is really all about covalent bonding at a higher level than what we initially covered in chapter 3. So the first topic is how we can use the Lewis structure to predict three-dimensional shapes. So Lewis structures will be covered on the first exam, and if you don't know how to do that, you're going to really struggle with chapter 4 as well. So the first thing we're going to do is using those Lewis structures to predict the shape of the molecule. And the method we use to do that is called VSEPR, sometimes pronounced as VSEPR, even though it's not really spelled exactly like that. But what it stands for is valence shell electron pair repulsion. Now, what this approach essentially does, it's not even like there's not even a lot of chemistry involved. I mean, you have to know how many valence electrons are on the center atom. That comes from chemistry. But then once you have that sort of out in front of you as a Lewis structure, all you're doing in this method is you're placing the valence electrons around the center atom as far away from each other as possible. So it's purely a geometric approach. It's that we have so many pairs of electrons around our center atom, depending on what the structure of that molecule is. How do we get them as far away from each other as possible? Because again, electrons repel each other, so they want to be as far away from each other as possible, and that's what this approach does. All right, so then when we do this approach, there's going to be two sort of classifications that come out of it for each molecule, and there's not limitless possibilities. It's, for the types of molecules we're covering, there's a kind of a defined structure space you're working in. But the first of those terms is called the electron group arrangement. And this is going to be the three-dimensional geometric shape that all of the valence electrons occupy, the bonding and the non-bonding valence electrons around the center atom. So your center atom is going to have some number of bonds to the outer atoms, however many of those there are. And in many situations, although not always, the center atom could also have some non-bonding electrons, some lone pairs. And the shape that all of those valence electrons occupy is referred to as the electron group arrangement. And there's really only 5 possibilities that you'll have to know for that. Your center atom is going to have somewhere between 2 and 6 pairs of electrons around it. And that total number of electron pairs is going to define the electron group arrangement. But then usually the more useful term to talk about in chemistry is the molecular shape, or the molecular geometry as it's sometimes called. This is the three-dimensional shape that only the atoms occupy. So it basically ignores the lone pairs on the center atom when you define the molecular shape. And there's more possibilities for molecular shape because each electron group arrangement is going to have some number of molecular shapes that kind of fall under that, which depend on how many lone pairs the center atom has. So you can think about this as what the molecule looks like, because when we visualize molecules, and in most of the experimental techniques that we use to visualize molecules, which we don't really talk about a lot in this class, those experimental techniques can locate the nuclei of the atoms, but they can't localize where the electrons are. So you kind of ignore the lone pairs, even though they're there, and you're just defining the shape that the atoms themselves occupy when you're talking about the molecular shape. Okay, so those are the two terms that come out of this. Now, how do we predict which of the electron group arrangements and shapes we have? For that, we're going to classify every molecule that we come across with this type of notation, AXMEN. Now, I don't think your book covers it in exactly this way, but I kind of like this approach as a way of organizing and classifying things. So in this notation, A is basically just a placeholder. It just represents your center atom. Every structure we're going to talk about in this part of the course has a center atom of some sort. So you just have that A there to indicate that, but nothing changes about that. But then the important parts of these are what is X and E referred to. So in this formula notation, X is an atom that's bonded to the center atom. So one of the it's however many outer atoms there are. So that you can get from the chemical formula, right? So if you have PCl3, the one we did in class last time, phosphorus is a center atom, and there's 3 chlorines around it, so there'd be 3 X's in the formula. But then E is the number of lone pairs in, around the center atom, which again, in the chemical formula, we don't define that, but for this notation, we need to include it because that's going to determine both the electron group arrangement and the geometry. So then in this formula, the M and the N that I've indicated are subscripts that tell you how many of each you have. And in general terms, X and E are referred to as electron groups. We said that the electron group arrangement is the shape that all of these occupy, and so all of these X's and E's together are referred to as electron groups. We always treat everything as sort of pairs of electrons still, and each of those pairs, whether it's bonded or non-bonding, will be classified as an electron group. Okay. Another term that, again, your book doesn't use, but I like it, is what's called the steric number. This is given as the sum of those two subscripts, M plus N. It tells you the total number of electron groups. And as we'll see in a little bit, that defines what the electron group arrangement is. And the possibilities are basically 2, 3, 4, 5, or 6. There's only 5 possibilities that you have to really worry about. So M plus N, the sum of those two, is the total number of electron groups. Now, one thing to keep in mind as we do this, though, is that in this VSEPR system here, the bond order between A and X. So again, X is an atom that's bonded to the central atom A. It could have different bond orders, as we talked about last time when we drew the Lewis structures. But for VSEPR, the bond order between A and X does not matter. Whether it's a single bond, a double bond, or a triple bond, that X will just count as one electron group. Now, we'll talk a little bit about how if there's multiple bonds, double or triple bonds, that can have small impacts on the shape. But the general broad classification, identification of that shape does not care whether the X is singly, double, or triple bonded. So from that standpoint, when you're drawing a Lewis structure for the purpose of VSEPR, you don't even really need to get all the double and triple bonds correct. As long as you have the number of atoms around the central atom, which comes from the formula, and the correct number of lone pairs on the central atom, that's the important part. You don't have to worry about all the bond orders and formal charges and things like that. That's not going to come into play when you're doing VSEPR. It's just how many things are bonded to the central atom. All right, and then another term from VSEPR that comes out of this is the bond angle. So we're going to classify these shapes in terms of their names, but also to help us understand them better, we're going to define some angles that are involved in them. And this is going to be the angle between two of those outer atoms, two outer atoms that are bonded to the center atom, with the center atom as the vertex. All right, so as an example, we're going to learn from the stuff we learned today, it'll be very easy to predict that water, H2O, has sort of this bent shape to it. The hydrogen atoms are not pointing out in opposite directions. They're bent like this. And this angle here would be one that we could define once we know what the shape of that is in more detail. Okay, so that angle, which is sometimes abbreviated as the HOH angle, so a little angle symbol with HOH, 3 atoms that are involved, we're going to be able to talk about what that angle is, the approximate value for it, and how we can predict that based on the electron group arrangement and the molecular shape. Okay. All right, so that's kind of the general background information and terminology. The best way to learn this, I think, is to just go through all the different possibilities and visualize them. So I highly encourage you. I'm going to try to use it today. Sometimes this simulator slows down my tablet to a unsustainable level. I hope that doesn't happen today. But when I'm trying to run Teams and all that at the same time, especially. But this simulator that I've linked here in the notes is exceptionally good for learning this topic. Because to appreciate this topic in full, you have to be able to visualize things in 3 dimensions. Now, I'm a mediocre artist at best, so I can't really draw very well in 3 dimensions. And no matter how good you are, trying to draw things on paper in 3 dimensions is always tricky and always requires some skill to be able to do it and to visualize it. So this simulator allows you to see things in 3 dimensions, sort of rotate them around on your own. It really allows you to appreciate these shapes a lot better than I can just draw them on a lecture slide. All right, so let's go to it and let's see what happens. So we're going to start with, as I said, there's 5 possibilities, 2, 3, 4, 5, 6 electron groups. We'll get through the first 3 or 4 of those today and continue it next time. So with 2 electron groups, so this is what the simulator looks like. You can do it with real molecules or models. I'll do models today. All right, so this is the first one that comes up, 2 electron groups. And again, the idea here is that we want to be able to put the electron groups as far away from each other as possible. So geometrically speaking, if you have 2 things on the center atom, and you want them as far away as possible, they need to be at a 180-degree angle, completely linear. So with 2 electron groups, your electron group arrangement will be linear. And if both those electron groups are atoms, then the geometry is linear. So that's what linear looks like. It bends a little bit as I rotate it, but it's totally 180 degrees. If you replace one of those with a lone pair, again, the lone pair can also be thought of as an electron group, and it just goes exactly opposite where the bonded atom is to maintain that linear arrangement of the 2 electron groups. Okay, so that's what we would have for 2 electron groups. So one thing to keep in mind if, see here we are already slowing down. I could try to open this, or just open and close it a million times, I suppose, is another way to do this. I could try to open it on the podium monitor and have to switch back and forth, but I don't have it queued up yet. So I'll try to do it this way, just open it a million times. Okay, if there's no lone pairs on the central atom, the electron group arrangement and molecular shape are the same. So if it's AX2E0, AX3E0, no lone pairs on the center atom, the name that you give for the electron group arrangement and the name that you give for is the same as the molecular shape. They're identical to each other. So that's true for AX2. So as we saw in the simulator, AX2 arranges the 2 outer atoms 180 degrees apart, and we call the electron group arrangement linear whenever there's 2 electron groups. So it's going to be a linear arrangement when there's 2 electron groups. And in this situation where it's AX2, the geometry is also linear, and that gives you a 180-degree bond angle. Now, there are some molecules that would be classified as AXE, but these are trivial because from a geometric standpoint, if you only have 2 atoms in the formula, they have to be linear. There's no way to make 2 atoms not linear if there's only 2 of them. So you don't really need to think about this one too much anyway. But if you had an AXE, what you would do is it'd still be 2 electron groups. So they'd be 180 degrees apart, but one of those is a lone pair. One of them is an atom, right? So whenever there's 2 electron groups, you have a linear arrangement. In AXE, one of those 2 is a lone pair, but the geometry is still linear because there's only 2 atoms. That's all it can be. And there's no bond angle here because you need 3 atoms to define a bond angle. So not applicable for bond angle. And again, this is trivial. So if you see this, all diatomic molecules, which are molecules that only have 2 atoms in the formula, whether it's 2 are the same or 2 different, all diatomic molecules have a linear geometry. So H2, O2, N2, CO, NO, whatever formula you can think of that only has 2 atoms in the formula has to be linear because 2 atoms cannot be anything but linear. Okay, so those are the pretty straightforward ones, I would say. When we go to 3 electron groups, the electron group arrangement in this case, anytime you have 3 electron groups, well, let's see what that comes out to with our simulator. So we're going to do AX3 and AX2E here. All right, so if we go back to that, all right, so now we're going to add an electron group. So to do that, you just touch it again. And we want to put those 3 electron groups as far away from each other as possible. It still ends up being best to do it in 2 dimensions and not make a triangle, or what's going to be referred to as trigonal planar. So you put these 3 electron groups as far away from each other as possible. And anytime there's 3 electron groups, any combination of atoms or lone pairs in the center atom that add up to 3, they're going to arrange themselves in this way, 120 degrees apart in a perfect triangle like this. So that's AX3, where all of those electron groups are atoms. And then if we go to AX2E, which is the other one on that slide, we're going to replace one of these three atoms with a lone pair. Now, for most of the geometries, all of these outer positions are equivalent, so it doesn't really matter which of those we choose to replace with a lone pair. That won't be true for some of the later ones we do, but for the ones today, these three positions are all equivalent, so any of those three can become a lone pair. So again, these three positions are all trigonoplanar. They're totally flat, 120 degrees apart. And then if we just replace one of those with a lone pair, we get the AX2E structure, which looks like this. Where again, all three of those groups make a triangle. One of those three is now a lone pair. And you're left with just the three atoms in this sort of bent shape like that. All right, so to summarize that, and we're still slow here. So for AX3, if all of them are atoms, yep, we're going to be painfully slow, so I have to do this again. You put those three atoms still in 2 dimensions, but 120 degrees apart now to put them as far apart as possible. And again, the electron group arrangement, anytime there's three, is called trigonoplanar. And if all three of those electron groups are atoms bonded to the center atom, there's no lone pairs involved, then the molecular shape is also trigonoplanar. So again, in those situations where there's no lone pairs, the electron group arrangement and the molecular shape are the same. So that's trigonoplanar, and the bond angles in this case are 120 degrees. All right, you have basically three angles in 2 dimensions. So if you want to go all the way around, that's 360. Each of those is 120. All right, so that's trigonoplanar. And then if we go to the other possibility, which was AX2E, when you have AX2E, the total number of electron groups is still 3. 2 X's, which are 2 atoms bonded to the center atom, 1 E, which is 1 lone pair. So because there's 3 total, you're still going to put them in a trigonoplanar arrangement, all 3 of those. But now one of them is a lone pair. As I said, in most situations, starting with this one here, all 3 of these positions are equivalent, so you can put the lone pair wherever you want. It doesn't really matter. I'll put it at the top for no particularly good reason, and that leaves the X's down here. So the name of this molecular shape, again, the molecular shape only looks at what shape the atoms themselves occupy, ignores the lone pair. So now you have 3 atoms that are sort of in that arrangement, and we call that bent, or you might see sometimes V-shaped. Bent is much more common, but you might see it's called V-shaped as well. What you should be aware of is if you have 3 atoms in the formula, we'll talk about this, we'll kind of summarize it at the very end next time, but if you have 3 atoms in the formula, your only 2 possibilities are linear and bent, because you have the center atom, you have 2 around that, and those 2 atoms can either be straight out linear, or they can be pointing at an angle bent. So whenever that formula has 3 atoms in it, that's the only 2 possibilities. AX2E is one that gives you the bent arrangement. Now, what happens to the bond angles in this case? So the bond angles are still close to 120 degrees because this is a trigonoplanar arrangement. But this is the first time where we have to talk about the influence of the lone pairs. So the lone pairs are not held tightly between 2 atoms. They're kind of floating around out here in space on the central atom. So whether you can fully rationalize this or not, lone pairs have stronger repulsion than the pairs of electrons that are in bonds. So this lone pair is going to sort of push down on both of these atoms like this. There's more repulsion from the lone pairs. So that's going to compress your angle a little bit. It's going to be a little bit less than 120 degrees. We can't say exactly how much less. That's hard to predict, and that depends on what atoms you're talking about. But we expect the bond angle to be a little bit less than 120. And it's usually only like a few degrees at most. I'll give you maybe some real examples later on, but so maybe like 117, 118. It's not going to be like vastly different. But when you have lone pairs involved, they have stronger repulsion. They push down on the bonds that are next to them, and that's often going to then cause a compression of the bond angles by a little bit. That's what we see here. All right, what we're going to end with today are 4 electron groups, so 3 possibilities with 4 electron groups. This is the first time we think in 3 dimensions, which may or may not be your strong suit, depending on your spatial abilities, I suppose. But if we go back, let's look at the possibilities then with 4 electron groups. All right, so when we put 4 electron groups in, this is the first time that the shape is no longer flat. It has 3 dimensions to it. And there's different ways of sort of thinking about this. But the name that we give it, actually, they allow you to put the name in here. I didn't notice this. So that's I don't know if you can read that from that far away, but the name that we give for the electron group arrangement is tetrahedral. And then again, if it was AX4, the molecular geometry would also be tetrahedral. So we call this tetrahedral. The reason for that is, I don't think this gives you the option of doing it, but basically what you can do is if you, through each 3 atoms, you can draw a triangular face, and there would be 4 of those triangular faces around the central atom. So you would call it tetrahedral, is the shape. But there's also, you can remember it as 4 atoms bonded to the central atom, gives you a tetrahedral arrangement, so that's not too hard to remember. So that's tetrahedral. And then there's also going to be 2 possibilities where there's 4 total electron groups, but you have lone pairs involved. So you can have AX3E, where one of these atoms is now a lone pair. And just like the previous one, all 4 of these positions are geometrically equivalent. We'll talk about the bond angles as being in a little bit. They're all 109.5. You can show that here if you want. So bond angles are 109.5. All 4 of those atoms, all 4 of those positions are identically spaced with relative to each other. So when we put the lone pair in, we can put it wherever we want, is the bottom line. So if we take out one atom and put in a lone pair, you'll see that those 4 things are still arranged in a tetrahedral shape, but now one of those spots is occupied by a lone pair. And then what we call this shape is best visualized in this orientation here. We call it trigonal pyramidal. So basically a 3-legged pyramid, or a 3-legged stool is another way to think about it. We call it trigonal pyramidal when you have one lone pair up there. Okay, so that's the shape that we get for AX3E. And then if we put in one more lone pair and make it AX2E2, again, this is another situation where you have 3 atoms in the formula, so linear and bent are your only options. Because the bond angles are so close to 109.5, again, not exactly 109.5, but close to that, with the lone pairs involved, you would call that a bent geometry, bent and linear being the only 2 options when there's 3 atoms. But that's what it looks like. You have 4 electron groups, 2 of them lone pairs now. Those 4 occupy a tetrahedron, and the atoms that are left occupy sort of a bent arrangement. All right, so let's summarize all that then in the notes. So with AX4, the electron group arrangement with 4 electron groups, anytime there's 4, is called tetrahedral. So if all 4 of those are atoms, now the way that we draw this, again, it starts to get a little bit tricky because we have to think in 3 dimensions now. The way you indicate this is 2 of the bonds can be thought of as being in the same plane as the central atom. So you put them like that. And then if you draw a solid wedge like this, that indicates a bond that's sort of coming out towards you off of the page. And then if you do a dashed wedge like this, that indicates a bond that's going away from you. So again, there's no like perfect way of doing this. And I'm not the world's best artist either, but that's how we kind of indicate bonds that are out of the plane of the page. So tetrahedral, you have to think about it in 3 dimensions. So all 4 of those are occupied by atoms in the AX4 arrangement. And so that means the molecular shape is also tetrahedral. And unless you're really good at 3-dimensional geometry, this number is not going to be intuitive at all. But the bond angle that's associated with those is 109.5. So again, the angle between any 2 of these outer atoms going through the central atom would be 109.5 in a tetrahedral or electron group arrangement. That number is not easy to come up with, obviously. All right, and then if we go to AX3E, as I said, we can replace any of these outer atoms with a lone pair. So it's still going to be tetrahedral in terms of how everything is laid out. I'm trying to do this a little bit better than the last one, but we'll try. Let's see. That should probably be pointing down a little bit more than it was over there. All right, but anyway, that's the tetrahedral arrangement. And then one of those is going to be a lone pair. Any of those 4 positions is fine to put the lone pair because they're all equivalent to each other. But I'll put it at the top so we can see the name of the geometry a little bit better. The rest of those 3 positions are the atoms X. And then we would call this trigonal pyramidal. All right, and again, it's because these three atoms sort of occupy a triangle at the base, and then the A is above that triangle, kind of making a pyramid. All right, the bond angles in this case are still going to be similar to 109.5 because it's still a tetrahedral arrangement, but a little bit less because, again, this lone pair is going to push down a little bit more repulsive than the bonding pairs and kind of fold that up a little bit like an umbrella. Again, not a huge effect. So, the ideal tetrahedral angle is 109.5. If you have NH3 ammonia, which is AX3E, the bond angles in that are like 107. So it's like a couple degrees difference, okay? And then finally, if we go to AX2E2, there's sort of two ways of drawing this, I suppose, but we'll start with the more straightforward one that's based on what we did before. You have 4 electron groups. So it's tetrahedral arrangement. I still need to draw that better than I did. Went down a little bit. And this should be a little bit higher. All right. All right, so you have a tetrahedral arrangement of the electron groups. 2 of those are going to be lone pairs. And again, in this situation, all 4 positions are equivalent. So whichever 2 we choose as being the lone pairs is totally fine. That leaves the X's here and here, which is maybe not the best way to do it. Or if we turn this over on its side, kind of like this, put the lone pairs up there and there, then it's pretty obvious that this is a bent geometry. And again, some sources might say V-shaped. I don't think you'll see that in your assignments in this course. And for the same reason, because of the influence of the lone pairs, the bond angles are going to be compressed. And because there's 2 lone pairs in this geometry instead of 1, it's a bigger effect. So we said a typical AX3E structure like ammonia has bond angles of about 107. AX2E2, of which water, H2O, is one of the examples. The bond angles are like 105, I think. So another couple degrees smaller when you have 2 lone pairs instead of 1. All right, so that's the 2 through 4 electron groups. We'll come back next week with numbers 5 and 6, which are a little bit more complicated, but still follow the same approach.